So in this section, what I really want to do is talk about how indicators work and then how you pick an indicator for titration. We're also going to start looking at polyprotic acid titrations and get a better feel for indicators by looking at picking an indicator for a polyprotic acid titration, because it turns out that's probably one of the harder things to sort of grasp in this whole thing, because we're so used to using phenolphthalein. Now, phenolphthalein, right, is an indicator for titration, and what are we trying to do with it? Well, we're trying to figure out what the end point is, and our goal is to try to figure out what the equivalence point is. So remember, when you have a titration curve, you're going to have an end point and an equivalence point. The end point is where the indicator changes color, and the equivalence point is where the acid that you have in your flask, let's say, is equal to the base that you added as your titrant. And we're trying to use that to figure out the moles of acid or base that are in the solution. So, having said that, this is what phenolphthalein looks like at different pHs, and I made the lettering pink because that's the fuchsia color that you associate with an endpoint, right? So we're titrating a weak acid with phenolphthalein, and what happens is that phenolphthalein and all indicators are essentially weak acids or weak bases. So phenolphthalein turns out to be a weak acid. And when it's sitting in the solution, right, what happens is you're using up the hydronium during the titration. Remember, a titration curve shape looks something like this, right? Oops. Darn it. Looks something like this, where it's going up in pH and it goes like this. Remember, the equivalence point on a weak acid, 7's down here. The equivalence point is up above 7. And this is pH on this axis, and this is volume of titrant down here. Okay, so what's happening is phenolphthalein is a weak acid, and it's responding to the change in hydronium concentration. So as you remove the hydronium by adding sodium hydroxide, right, neutralization, you're removing the hydronium. What ends up happening is the color gradually changes around pH 9. Okay, so if you've done enough of these, you'll know that sometimes it's really like pink, and sometimes it's really dark pink, like it is like over here, right? And it's colorless everywhere before that. And really, what's happening is as you're titrating your acid, right? You're not titrating the phenolphthalein. You're titrating your acid. The pH eventually jumps up high enough that the phenolphthalein will change color. Now, the transition from colorless to colored for phenolphthalein depends on phenolphthaleine's pKa. So it's the pKa of the indicator. This is one of the things that confuses people. So your phenolphthalein has a pKa. Whatever you're titrating has a pKa as well. And the equivalence point for your titration, you want it to be close to the pKa of your indicator. So let me explain to you sort of why that is, right? It's because if you think about a titration curve, here's my equivalence point, right? And then I'll relate it back to phenolphthalein. When you're here, midpoint, you have an equal mixture of HA, that's 50%, and A minus, that's another 50%, that's the other half, right? You've converted half of it over because the moles of acid, right, and base are the same here, the added titrant. But here you've only added half, so you've converted half of it over. Now, the same thing is happening to the indicator, but for phenolphthalein, this is colorless, and this is bright pink. So this has color to it, right? And it's fuchsia is the color, but indicator, generally you have two different colors. One of the colors that might actually be colorless, so that's kind of weird, but the other color will be something bright typically, and those are really kind of the easiest indicators to use. But here's the main idea: you're converting over, right, the indicator from its colorless to colored form, and we know the pH at which this happens because the midpoint pH, right, is the pKa. So this transition goes at the pKa of the indicator. And so you go from colorless to bright pink. Now remember, whatever you're titrating might have its own pKa. So what our goal in picking a indicator is to match the pKa values. Okay, so I put this on a couple of different titration curves. These are the same ones from the last set of slides, really. I just copied it over. And again, we have a strong acid and we have a weak acid. And the thing about a strong acid titration is it starts at this low pH and then it rapidly rises to the high pH. Remember, this pH is determined by titrant. So it's really dependent on the molarity of the titrant, and it's the excess titrant, right? So it turns out it will be pretty close to whatever the pH of the titrant is. This one would be 13. You can see how this is very closely approaching 13. Even when you're back here, it's pretty close to it. It's near 12.5. So no matter like what the indicator is, typically a strong acid base will transition far enough that any indicator will really give us a pretty good idea of the equivalence point. Remember, equivalence point for strong acid base happens here, right? So this would be at 10 mils, but even if the color change was down here, it would be okay. Ideally, you want this to be near this value, and you want it to be in such a way that you can see the color transition. Right, and I'll talk about that a little bit. Some color transitions are harder to see. Now for this weaker acid, this one's pKa, I think was 5. Let's see, yeah, it was 5, because the midpoint's pH 5. This one actually matches the phenolphthalein really well, because this is where the equivalence point pH is, and you'll be seeing a color change right at the equivalence point pH. And that's kind of why phenolphthalein is so popular for weak acid titrations, because while it doesn't fit a strong acid-base titration pH that well, it doesn't really matter because this transition is so quick in terms of volume. But then for all weaker acids, it's a pretty good match because it changes here near the curvature of the titration curve, okay? All right, or right before it, really. So that's phenolphthalein. Now what we're going to do is look at a bunch of different titration curves and a bunch of different indicators. So I've listed several indicators here. This is phenolphthalein. This is actually thymolphthalein, and unfortunately I didn't put it over here. I meant to, but I didn't. Thymolphthalein is up here. It's actually even a better indicator for weaker acids. So like pH 4, phenolphthalein is really good. Typically acetic acid titrations, this is where this falls. But phenolphthalein wouldn't work if the pKa was really, really high. In fact, thymolphthalein might work, but you'll notice you're going to get a color transition here that is right around here, right? You'll start seeing it around here. So the problem is that's pretty far away from the equivalence point. And so typically really weak bases like this, it's hard to find a good indicator. Now, if you're looking at lower pH ranges, I was going to just show you these two. These two don't really work, and there's a couple of reasons why they don't work. And one is they're a little bit too low. So for sure, for anything that's a weak acid from 4 on up, these already have changed color before the equivalence point. The equivalence point is here. They're going to change color. This one will change color right around here. This one would change color right around here. But the other problem with this one, this is actually methyl red. Methyl red has a pKa of around 5, but you'll notice what happens. It's going from red to yellow. And when you're thinking about how the titration works, right? Think about phenolphthalein. It's colorless to pink. That's really easy to see. But from red to yellow, that's really hard to see because what you're going to be doing is having this bright red color, and then the yellow is going to be appearing inside of it. So it takes a little bit more thought to pick indicators than just like, let's add phenolphthalein. But the truth is phenolphthalein works pretty darn good. All right. But things like methyl red or thymolphthalein, when we use them, we have to be a little bit more selective in what we're using them for. So I thought I would put a bunch of these up here. I like this diagram. I believe it's from the textbook. It shows the color ranges, right, for a bunch of different indicators. There's also this one called universal indicator, which is a bunch of different indicators usually when people make it up, so that you can see the color changes for a bunch of different see colors different for a number of different pHs. So when you have a swimming pool and you're testing the pH of your water, it's actually the universal indicator that you're putting in. And typically, I think you're looking for this green color. Now, or maybe you're looking for slightly basic. I can't remember. I don't have a swimming pool, so I don't really know. Somebody with a swimming pool would comment. Anyways, but yeah, they have different forms, right? And the loss of a proton for phenolphthalein causes its structure to change, so that it gets a different color. And methyl red, actually, its neutral form is a base. So when you're adding titrant and you're removing hydronium, right, you go from this dark red color to this yellow color. And like I said, this transition going from left to right here is really hard to see. But if bromocreosol blue is a good one. Res azurin, which is actually not really used that much for titrations. It's used for biological assays. But it has a color change. This one would be hard to see because the colors aren't that distinct. But bromophenol blue would have a fairly distinct color change, although the pH range is a little bit on the low side. Generally speaking, is you want to have the color change occur within you want to pick the color change to be within about 1 pH unit of the equivalence point. So typically what you do is you guess at where the equivalence point pH is. You can calculate it, but most people don't spend the time to calculate it because it's pretty easy to estimate where it's going to be. And then you pick an indicator whose color change is easy to see, right? That is, goes from a light color to a dark color, for example, and is near that equivalence point pH. The pKa of the indicator is near the equivalence point pH. Another way, there's a lot of different ways people visualize this. One is people will cite what the range of the color change is. That's okay. But also, it's really useful because these are easily found. The pKa's of the indicators are good measures of where you would use that indicator in terms of equivalent point pH. I like this graphic. It's from ChemGuide. It's a fairly reliable source. I like their information. It doesn't always fit our courses because it's from the UK, but this is a nice visualization of how the color changes with pH. So like for phenolphthalein, if you had this sort of chart, you could easily see like, oh yeah, this pH, anything around 8 or 9 would be good because that's when the color would change. So if your equivalence point pH is near 8 or 9, that would be a good one. Litmus, which is probably one of the most commonly known indicators, is right around 7. I think its pK is just below 7. And so what happens is if you want to know if something's acidic, right, then you could put a piece of blue litmus paper in it and it'll turn red. If you want to know something is basic, what you're going to do is take red litmus paper and stick it in there and you'll see it turn blue. And really all that litmus paper is the dye, either with a slightly basic treatment or a slightly acidic treatment, and then when you stick it in, they switch colors. So it's a real easy way to see whether or not quickly is something acidic or basic. Methyl orange, right, you would see like, oh yeah, this would be a good indicator around pKa or equivalence point pH 5, but it's probably best for bases because in a base, if you remember, the titration pH goes like this, and if this is 7, the equivalence point is always just below 7. So methyl orange would be a good one for titrating bases, simply because it goes from this really light color to this dark red color at the end point of the titration. Yet another summary. I can't remember where I stole this from. I don't think I looked all these up individually, but years ago I stole this from somewhere. I've seen this chart around the internet. But a bunch of different indicators, their colors, and then the transition from low pH to high pH. So like thymol blue, right, in its base form would be yellow down here. So this is actually a really low pH. Now it's called thymol blue because it actually, the most common use of it is when it goes from yellow to blue, and this is an easy transition to see, but this one would be a hard transition to see unless you're going from the high pH side to the low pH side. Its pKa is so low though it's not really that usable. It's kind of specialized. Most of the rest of these could be used for any strong acid-base transition as long as the color direction of the color change fits like what's easy to see. So if you're doing a strong base with a strong acid, then it's going to go from the base form yellow to red, so methyl red would be a good one again. But if you're going the other way, then any of these going to any of these colors seems to be like a fairly good choice. So, you get questions often on a quiz or in homework, like pick an indicator, and students are usually stumped because let's say the equivalence point pH is 7, right? Well, which one do you pick? Well, you could pick any of them. There's like many, if the equivalence point pH is near 7, there are many that fit that category in here, right? That you could pick, and any one of them is probably okay. Even phenolphthalein, which is way pKa is way out of the range, works fine too. Now, having you talked about litmus paper, right? Litmus paper is just acidic or basic. You could probably have guessed that they make pH paper, is what they called, for a lot of different pH ranges, and there's single strip, okay, and a single strip is actually just a roll, like of paper, and then all you do is you put a little bit of the solution on it and you match the color to the chart, and so you can tell what the pH of the solution is. Sometimes when people are doing swimming pools, like I mentioned, you can add universal indicator. This is really kind of a universal indicator that's in the pH paper, and so you can just stick this into your swimming pool water or drip some swimming pool water onto it, and then what you'll see is the color associated with the pH. And they have a lot of different varieties of this. So let's say you wanted to know the pH between 4 and 7. You could probably get half pH unit paper for that. So it would be going like 4, 4.5, 5, and there would be a whole series of colors just for that range. And a different, it's a different container of paper, different variety of the paper, but essentially works the same way. The other type of pH paper which has become really popular is this stick type, and I actually, for the most part, don't like these because they're a little bit harder to use, and it gives you that feeling like you should just stick this in your solution and measure the pH. And if that's appropriate to your application, it's great, because what you get is you get 4 ranges of colors that tell you what the pH is, and so you can have it's really easier to read because you're just matching 4 different colors. It's like a barcode. What I don't like about it, though, is if you're actually doing like a chemical reaction, you want to know the pH, you got to put liquid on each one of these spots, because it's never good to stick pH paper in your reactions, because a lot of times these indicators, right, they're weak acids, weak bases, they'll dissolve and contaminate your reaction. So that's kind of why I don't like them. I think for most part, like this strip type is the best for most of what we do in chemistry. And labs, that is for like Chem 1A, 1B. And in OChem, we use them all the time in organic chemistry for like measuring reaction pH. But this is the type that we use over here, this sort of the strip type. Okay, so this is what a polyprotic acid titration curve looks like, and it really is like a monoprotic. It just has two humps in it. So why does it have two humps? So the reasoning for that is because you have a weak acid, and I have some of this sort of summarized on the next couple of slides. You have a weak acid that has two protons that are ionizable. That is, you can pull them off, and they are in generic form, something like this. I have H2A, right? And I'm going to titrate that, or I'm going to let it ionize with water. It's however you really want to visualize it. You'll get hydronium, right? Plus A minus, HA minus. So this is actually the reaction associated with Ka1 or pKa1. And then there's a second ionization, and that would be HA minus plus H2O. And that makes H3O plus and A minus, A2 minus actually. And this is the reaction we associate with Ka2, and these two happen independently of each other. And this is sort of the way we talked about it in the acid-base chapter. When you have polyprotic acids, the Ka values for polyprotic acids are usually far enough apart that we assume sort of sequential ionization or independent ionization. That is, this acid will completely ionize before this acid does. Now, during a titration, what you're doing is you're adding a base to a weak acid, and that removes hydronium. And since Ka1, right, is so much bigger than Ka2, that is, this first acid is so much stronger than the second acid, you're actually able to remove all the hydrogen ion, all the hydrogen ion, from the H2A to make the HA minus before you start removing any from the second ionization. So this happens first, and then in sequence, this will happen. So if you're thinking about what the curve shape looks like, right, there's a couple of notable landmarks. One is the pH at midpoint. Now, in a monoprotic acid titration like this one, right, these all have one midpoint pH. So in a polyprotic, because you have two Ka values and they happen essentially independent of each other, you have two midpoints, right? So this is midpoint 1, and this is midpoint 2, and you also have two equivalence points. So the first equivalence point is here, the second equivalence point is here. Oh, yeah. What does that? It just wants to change slides on me. Okay, so there's the second equivalence point, and as you're titrating, right, this volume to this volume, right, is 20 mils and 40 mils, is exactly double the first one, simply because you're titrating the same acid. So in the first titration, what you're doing is you're converting H2A to HA minus, right? And at the first midpoint, that is right here at this volume, you've converted half of it over to the HA minus form. So it's like 50-50 at the midpoint. At the first equivalence point, it's 100% HA minus. I said 100%. There we go. Now, when you're doing the titration, if you continue on, right, then what will happen is you'll get a second equivalence point. Now, at this point here, though, before the second midpoint, you have HA minus, and then you go to A2 minus. But right here, right, this is half and half HA minus and A2 minus, and then here it's all A2 minus. And this pH here, just like it was in weak acids, this is determined by titrant. Okay, so what else do I want to say about this? Oh yeah, so the pH, it's all this stuff that's on here. I actually have a nice clean slide with all this typed on there, but I just like writing it on the slide. Right, that pH, this is pKa1. And this pH is pKa2. Now, when you're going to be picking indicators, it's important to know not the midpoint pHs, but it's important to know the equivalence point pHs. So what are these pHs, right? Maybe I use a different color pen. Wow, that's genius. It only took me like a year to figure that out. Okay, so this is what's important to know for the indicator selection. Sorry, just thinking how stupid I can be sometimes. So what is that pH? Well, this turns out this pH looks like it's halfway between pKa2 and pKa1. It's exactly halfway between, like mathematically can be shown, that kind of thing. So pKa1 plus pKa2 divided by 2. I know. Sandwich. That's going to be your pH for your first equivalence point. And your second one we can estimate based on the titrant, right? And the second midpoint. So this is going to be pKa2 plus pH of the titrant divided by 2. And that's a pretty good estimation of where that color change will be. So just to summarize what I was writing on there, and I'll show you a nicer picture of all this. Similar to monoprotic acids, right? Multiple Ka values because you're doing successive ionizations is the term that we use, right? And each of the ionizations, right, get successively weaker. So the second ionization happens only after the first ionization is completely done. The midpoint pH values are the same as the pKa's, just like they were for monoprotic. And then the first equivalence point pH is the average of pKa1 and pKa2. You can simultaneously solve the equations using the computer, but we typically assume successive ionizations, just like when we did the calculations for polyprotic acids in the earlier chapter. The other thing that I didn't write on here, because this is not a general thing that people teach, but the pH of the second equivalence point is basically the titrant pH, which is typically 13 for like 0.1 molar sodium hydroxide, plus pKa2 divided by 2. And that gives you a pretty good estimate. And these are the things that we need really to understand, like what indicator we're going to pick, right?